Hey friends, here we are in the last lesson of this unit and modeling problems using quadratic functions. So applications, real life applications of quadratics that come up. So make sure you got your graphing calculator. It's always a handy thing to have with you. It makes life a lot easier in some cases. So here we go. Here's a pretty standard looking question. The path of a volleyball can be modeled by the function this, where d is the horizontal distance in feet and h is the vertical distance, also in feet. To determine the maximum height the ball reaches, which part of the vertex would I look at? Well, because this is in vertex form, I have the vertex, it's 9, 8. I don't need my graphing calculator for that. I would look at the maximum height is the y coordinate. And so the max height is 8. To determine the horizontal distance it takes the ball to reach its maximum height, I would look at the x coordinate. That's of the vertex. So the horizontal distance is 9 meters. Or 9 feet, I guess. Okay, so that vertex, again, if I know it in vertex form, it's pretty easy to work with. To determine the horizontal distance the ball is in the air, what part of the graph would I look at? Well, that is going to be this graph. We'll draw it in a second here, but again, just think of it. It's going to look like that. Well, I want to find that part right there. So I want to be very specific here. That's the positive x-intercept, right? Now, how do I find that value? Well, I'm going to go and graph this thing in my calculator. So you go do that too. Let's go and put this function into our calculator. So hit pause, graph it, and let's see if you can find that x-intercept. See you in just a moment. Okay, so I've gone and I've put this in my graphing calculator, and notice I want to find that x-intercept. So I've got y2 is equal to 0. And I hit graph, and geez, I don't have a very nice graph. And sometimes this is the trickiest part of the question. So what we'll do is we'll go to our window settings, and we'll just kind of analyze what we've got here. Well, x-min, x is horizontal distance. The smallest horizontal distance I can ever have is 0. Now, it looked like we needed to go further to see where this ball would hit the ground. So I'm just guessing here. I'm just going to go big, say 25, and I'll make my scale, say 5. Now, y-min is the vertical height above ground. So the lowest height above ground I can ever have is 0. And the max in this question was at 8. So I'm happy with 10 because that's where our vertex was at 8. So now I hit graph. Notice my x max where I hit the ground. It's just a little tight still. So see how it's just a bit of a guess. So I'm just going to go back and I'm going to make that say 30. And that should do it. So sometimes you've just got to do what I just did. Just play around with your window settings just a little bit before you can find what you're looking for. Okay, we want that positive x-intercept. Second, trace, intersect. First curve, second curve, guess, who cares? Boom. And so to the nearest tenth, we would say 25.32. So once we got those window settings set up, these are actually pretty straightforward questions. It's just about getting that window setting. Okay, so our positive x-intercept was, what did we say, 25.2, I think is what we said, 25.3. So the horizontal distance the time is in the air, or the horizontal distance the ball is in the air is 25.3 feet. To determine the initial height, okay, the initial height is the y-intercept of our graph. So again, all I'm going to do is I'm just going to go back to our graphing calculator, and I'm going to find that y-intercept. So you can just go second, trace, and then you see the first one there says value. Let x equal 0. Boom. The initial height was 5.5 7 feet. There it is. So again, the initial height is the y-intercept. So that's at 5.57 feet. Okay, number 5. How high was the ball in the air when it had traveled 2 feet? Okay, well, how high? Well, that's the y value. When it had traveled 2 feet horizontally. Well, that means I'm going to let x equal 2. So I go back to my graphing calculator. So you can see this is all just calculator driven here. Go back to my calculator and I say second calc value, and I'm going to let x equal 2. Bingo. 6.53, just like that. There we go. 6.53 feet. And on a test, it would tell you what to round to. Okay. Now that one's easy. I like it's easy-ish, but 6 is the one that sometimes we struggle with. And a lot of these questions you'll see again in 30-2 for your diploma. How far horizontally? Well, that's an x value. Had the ball traveled while it was above 6 feet? Well, that's my y value. So on this one, what we do is we go back to our graphing calculator and we want an x and we know a y. So what we do is we go to y equals, we go down and we graph what we're looking for. We want how long is the ball above 6 feet? And you can see it crosses twice, it intersects twice. So what we need to do, friends, is find both of these points of intersection. So second calc intersect. And again, this whole first curve, second curve guess. So one of them is at 17.2. And then what we're going to do is we're going to go and we're going to find the other one. So we repeat the process, second calc intersect. And unfortunately, with the TI calculator, you got to move it all the way over. Okay, some of you might have a Casio calculator. It does it a heck of a lot quicker. You go enter, enter, enter. And the first point of intersection really is 0.8. I'll go to the 100th, 4. Well, how long is it above 6 feet then? Well, what we just found is we found 2 points. We found the second point of intersection was at 17.2 feet. We found the first point of intersection was at I'll just keep to the 10th, 0.8 feet. So how long was it above? Well, what we're going to do is we're just going to subtract these two things. So 17.2 minus 0.8. It traveled 16.4 feet horizontally while it was above 6 feet vertically. There we go. Okay, so that's a really good question. We see that one again at 30-2. All right, write the domain and the range. Okay, so application questions. We just have to be careful that this graph, I'm just going to go back up here, it doesn't go on forever, right? It stops when that ball hits the ground. And I don't want to use x's and y's in the function, it's d's and h's. So here we go. So for the domain, that's the d as they've got it labeled. It starts at a horizontal distance of 0. And where does it stop? Well, it stops when it hits the ground, which was 25.3 feet. D is an element of the rails. The range, well, that's the height above ground. So the smallest height above ground ever is 0. And the highest height above ground from our vertex was 8. And H is also an element of the rails. Okay, so this question here is something you're going to see this year in quadratics, and I promise you, you're going to see it again when you take 30-2. Very, very important question. So all calculator driven, really, most of the time in these ones. Okay, so it's number 8. I guess that sounds like number 2 to me. Okay, this is a very, very common question as well. So quadratic functions can model revenue, and that's what this one is here. So it says a dinner theater has 600 season ticket holders. The owners of the theater have decided to raise the price of the season ticket from the current price of $400. According to a recent survey of season ticket holders, for every $50 increase, 30 season ticket holders will not renew their seats. What should the owners charge for each season ticket in order to maximize their revenue? So they're going to jack up the prices, but when they do it, they're going to lose some people. Well, what this looks like is this. The profit or revenue is going to go up until a certain point, and then people are going to say, it's not worth it. I'm not paying that price. So here's how we do this. What we're going to say is we need an unknown. We need a variable. And we're going to call that variable x. And I'll get to that in just a second. Okay, we're going to let x be something. But when I want to figure out revenue, here's all I want you to think about for revenue. Revenue is simply this. It's how many of an object I sell times how much money I sell it for. So originally, this theater company was selling 600 season tickets at $400 each. That was the original revenue. So that would be, $240,000 or something. So now they're increasing the price. So I say to myself, let's go back to numbers. Numbers. Well, every time they increase the price, 30 people will not renew, minus 30. And they're increasing the price by 50 plus 50. Okay, but we don't know how many times they're increasing the price, and we don't know how many groups of 30 people won't renew. So here's the really, really, really important part. We're going to say X. What does X represent? Let X be the number of ticket increases in price. Ticket price increases. I should have got the word price in there. Whatever, dollar bills increases. Okay, that's what that means. So now that we've got our function right there, guess what? All we've got to do is go and graph this thing. So let's go graph this thing. So here we go. Let's put this into here. So our new function, let's clear everything out. And for giggles, let's go, I like bright green. Let's go here. Okay, what do we have? We had 600 tickets minus 30x. And we had 400 plus 50x, just like that. Okay, and we go ahead and we hit graph. And, oh, I put that in the wrong function. You see all that shading? Okay, I just got to go fix that right there. Give me just a half a sec. So what I did there was I did some shading with inequality, and we don't do that in 20-2. I was clearly working with something else. Okay, try that again. Graph. What the heck? Look at that. I don't see anything. Our window settings are really bad. So let's go to window. What is X? X is the amount of ticket increases. Well, the least amount of ticket increases is 0. The most, I don't know. I mean, I doubt they're going to increase the price 30 times. That would be $1,500 increase. So I'm going to maybe go 10. Okay, so see how it's just me kind of thinking about it? Y is the amount of revenue. Well, 0 is the least amount of revenue, but Y max? Well, here's what I'm going to do. The original revenue would have been 600 people times 400, $240,000. What I'm guessing is, I don't know, maybe that revenue goes up to 300,000. So see how I took the original revenue and then increased it? Then I go to my scale, and I'm going to make my scale really, really big, like 50,000. And let's hit graph. Let's see how we did. Hey, not bad. Like, I can barely see the vertex. So maybe what I'm going to do is I'm just going to go back down, and I'm just going to increase that vertex just like that. And you know what? I'm going to maybe just go a little bit further on my X max. Let's maybe go to 20. So you can see it's just a little bit of logic work, and hey, that's nice. Okay. So we want to maximize our revenue. Second, calc, max. Okay. And again, we just got to do this left bound. So you just got to hold it down. Sometimes it doesn't work for me very well on my emulator. So to the left of the vertex. Come on, you can do it. To the right. Come on, go. There you go. To the right of the vertex. And there it is. There's the max. So it's at 6,294,000. So our max, or our vertex, I should say, was at 6,294,000, like that. Okay, did we answer the question? What should the owners charge for each season ticket? Well, we didn't actually answer the question. What we know is this value here is our new max revenue. This 6 is how many times they're going to change the ticket price. That's the number of changes. Okay, so just ignore B. I shouldn't even have B in there. Okay, so how many times are they going to change the price? Well, they're changing the price 6 times, but each increase in price was $50, right? Each increase in price was $50. So what's our new ticket price? Our new ticket price then would be $400 plus 50 times 6. So our new ticket price, geez, they almost doubled it. Look at that, is $700. So the new ticket price will be $700. And when they do that, they are going to have a max revenue of $294,000. Not too bad. Okay. And don't worry about B. B wasn't supposed to be there. Bad teacher, forgot to cut it out of a previous question. Okay, so again, the max revenue question is a very, very common one. What you do again is you think of revenue as money and how many I'm selling. And then what you do is you've got whatever your initial amount was, how many you're selling. And then if you're going to increase, right? If more people are going to buy, right, then I'm going to add some amount. And if more people are going to buy, then I'm probably going to decrease the price. Or if I'm going to sell less, that means I've increased the price. So it's always going to be one's positive, one's negative. Okay, there it is, my friends. See you in the next unit.